Hello, everyone. This will be the recording for workshop number 2. And in this workshop, I'll go through a quick review for what you have learned so far, and then I'll solve some examples to help you for your homework number 2 and for the coming exam number 1. So what you have learned so far, let's say before week number 3, you were usually given a signal xt, continuous time or discrete time, and also given the output of a system, let's say yt. I'm taking here the continuous time, for example. You can assume it's correct for the discrete time as well. You have learned the properties of the signals. Xt is a signal, yt is a signal. You have learned the properties of those signals, and you know how to check if they are periodic, if they are odd or even, or how to write the signal, how to write a signal in terms of its odd and even parts. And then you were given the response or the output of a system, of an LTI system, linear time invariant. Which is the focus of this course. But let's say you are given an output and you have learned how to check if the system that outputs yt when the input was xt, you have learned to check if the system was linear or time invariant, and so on. Among other properties like memory or stability and so on. But so far we didn't talk about the system itself. You were focusing on the input and the output, and from those signals we had to check if the system is linear, time invariant, and so on. After actually learning about the properties of the signals, then learning about the relation between the input and the output. Is it coming from a linear system or a time invariant system, and so on. Starting from week number 4, you started learning about the system itself. Let's say we have a system, and now we'll assume that the system is always linear and time invariant. We have a system, we input a signal to this system, xt, or let's be more specific here, xn, because in week number 4 you were studying the discrete time signals and discrete time systems, and the output will be yn as well, discrete signal. And we want to know what kind of a system here, what kind of a response this system has to produce yn when given xn. And one way to find this response of this system is to input, instead of xn, let's input the unit impulse signal to the system, and whatever comes outside or output of this system will be the impulse, what we call the impulse response of this system. And this is very important to know, because once you know the impulse response of a system, then for any input you can find the output. And this relation between the impulse response and the input, the impulse response and the output can be obtained using the convolution. And in the case of the discrete signals, it's a convolution sum. So let's write it here. So if the input is xn and the system is an LTI system, this applies only to LTI systems. Just make sure about that and keep it in mind. So if the input to the LTI system is yn, then the relationship between yn and xn will be written in terms of a convolution, which can be written like this: xn convolution with hn. And as we said, hn is the impulse response of the system. Similarly here, and also, sorry, I want also to mention that any discrete time signal can be written in terms of impulses, unit impulses, this way. Xn is the summation from k equals minus infinity to plus infinity, xk delta n minus k. So we are shifting the impulses by k and scaling them by the value of the input signal at k. So shifted impulses and scale, shifted and scaled impulses, unit impulses. Let's take a quick example to make this idea clear. Let's say we have a speaker sitting in a room speaking, and let's say this is the room, which is, in our case, is the system, is the LTI system. And then we have someone listening here. The signal that's this speaker sending is xn. Let's say it's discrete, or just for the example. And this is the listener. And what this listener will hear is multiple copies of this signal because of the echoes on the walls of the room. So let's assume also, for the sake of simplicity, that the signal goes through only two paths from the speaker to the listener. One of them will be the direct path, goes directly to the listener, and we'll assume that it arrives exactly the same as it was transmitted, so without any delays and without any amplitude scaling or fading. And then we'll assume also another echo arrived to the listener after bouncing or echoing from one of the walls. Let's say it goes to this wall and then gets reflected or bounced towards the listener. And this copy of the signal, as it went through a longer path, it will be delayed. And after getting reflected from this wall, it will be also attenuated. Its amplitude will be less than the amplitude of this direct path. So the copy will be, sorry, let's say half x n minus 1. So it's delayed by 1, and then also its amplitude is half the original signal. So what this listener receives is yn equals xn plus half xn minus 1. Receives the direct path and a reflected or an echo, which comes, let's say, 1 second later, and with some attenuation. So as we said here before, to get the impulse response of a system, we input a unit impulse signal to get the impulse response of a linear time invariant system. So in order to get the impulse response of this room or system, we'll input, instead of the xn, we input just an impulse response. In this case, let's say the speaker just claps quickly his hands, and the listener is listening carefully to detect those two copies of the signal. So after inputting this delta n, the receiver or the listener will get this impulse response, which is an impulse at n plus a scaled and shifted impulse by 1. So half delta n minus 1. Okay. So this is the response, the impulse response of the system. And once we know this impulse response, we'll be able to get the output of the system for any other input signal, xn, any arbitrary xn signal. So let's just try make some visual representation of those signals. Let's say this is the input delta n. It's just a discrete signal, just one impulse at 0, and then it's 0 everywhere else. And the impulse response of the system will be, it can be written or represented like this. One impulse at magnitude 1 at 0, and another impulse with magnitude half at 1. This is in. Okay. Let me also write a explicit formula for this convolution between the input and the impulse response to get the output signal. Yn, as you said, it's the convolution between the input and the impulse response of the system, which is in discrete time signals is written as a sum from k equals minus infinity to plus infinity, xk h n minus k. So in order to get this output signal at any given time n, we need to do this infinite summation. And what we are doing here exactly is we do a time reversal on the impulse response, and then we start shifting it from left to right. This is in general. We'll see how to do it in examples. Yeah, let's do some examples to make things clearer. For example, number 1, let me. So what we are interested in, what you should be able to do after week 4 is, if you are given xn, if you are given the input to a system and its impulse response, you should be able to calculate its output for that given input signal using this convolution. And if given, when you if you are given the if you are given the output, if you are given an input and output, you should be able to get an impulse response of a system. Or I'd say you just need the output. And in this way, you just input an impulse, unit impulse signal to the system, and then you get the impulse response of that system, as we have seen here. You input the unit impulse signal, and then you get the impulse response of an LTI system. Let's see some examples. Example number 1. Let the input signal be xn equals half delta n plus 2 delta n minus 1. And we are given the impulse response of the system to be hn equals un minus un minus 3. Find the output of this system. For this, let's first plot these signals, the input signal and the impulse response of the system, just to have a better idea about the system that we have. Xn is two impulses, one of them at 0, and the other one would be at 1. One of them is scaled by half, the other one is scaled by 2. So Xn will be like this. This is n. This is 0. So we have an impulse at 0 with amplitude half. So it would be here. And then this should be 0. Sorry, this will be our second impulse. One at n equals 1. Then the impulse response of this system is the difference between those two unit impulse signals. Let's try to figure out what's the impulse response of this system. We have here n, and then this is the 0. So the first one is un, which is we know that it's defined as 1 when n is 0 or larger than 0 and 0 otherwise. So the un will be, let's use a different color. So it will be 1 here, and so on, and 0 otherwise. The second signal is minus un minus 3. So un minus 3 is the same as un, but shifted by 3 to the right. So it starts from n equals 3. And when n is larger than 3, it will be 1. Otherwise, it will be 0. And it will be, sorry, minus 1 because we have a minus here. Its amplitude is scaled by minus 1, let's say. So let's use another color for this one, black. So this 0, 1, 2, 1, 2, 3. So 3 is here. At this point, it will be minus 1, and so on. And then zeros everywhere else. So if we add those two signals together, we will have 0 here when n is less than 0. And we will have the signals will cancel out when n is larger than 3. So we'll end up with those 3 impulses only. So those will cancel. And those are already 0. So this hn can be written this way. Equals an impulse at 0 plus impulse at 1 plus an impulse at 2, 0, 1, 2, like that. So the signal at the end is just those 3 impulses, unit impulses. Okay, this HN. This is XN. Now, since this signal is 0 everywhere except those 3 impulses, we can quickly find the output of this system using this. It will be just the scaled impulse response. So xn is half delta n plus 2 delta n minus 1. So yn will be half hn plus 2 hn minus 1. And then we can substitute hn. So it will be half times hn is delta n plus delta n minus 1 plus delta n minus 2. So delta n plus delta n minus 1 plus delta n minus 2 plus 2 times delta n plus delta n minus 1 plus delta n minus 2. Okay. And then we'll have half and 2 here, 2.5. So 5 divided by 4, 5 4 delta n plus delta n minus 1 plus delta n minus 2. And this will be the output of this system. Actually, I have a little mistake here. This second term is time shifted by 1. So what we have substituted here is not correct. Let me correct it. So h at n minus 1. So we'll do a time shift on the impulse response. It will be instead of each n here, we substitute n minus 1. So it will be delta n minus 1 plus delta n minus 2 plus delta n minus 3. And the result will be half delta n plus half delta n minus 1 plus 2 delta n minus 1 will be 5 4 5 2, sorry, 5 2 delta n minus 1 plus 5 2 delta n minus 2 plus 2 delta n minus 3. So the output will be 4 impulses, one of them at 0, the other one at 1, and at 2, and at time 3, and each one is scaled, as you can see here, half, 5 over 2, 5 over 2, and 2. We can actually do this using that the long way, like using this relationship, yn equals xn convolution with the hn, the impulse response of the system, which is the summation from k equals minus infinity to plus infinity xk hn minus k. Now, if we look at xk and hk or hn, xn is only non-zero at 0 and at 1, and hn is only non-zero at 0, 1, and 2. So for the shifting, this xn will be non-zero only when k equals 0 and 1. So we'll do the calculation only on those terms, those two terms, which is x at 0 times h n minus 0 plus x at 1 times h n minus 1, which is exactly what we have done here. x0 is half times hn, and x1 is 2 times hn minus 1. And then we substitute and we find the exact same result. But when you see that the signal has only few non-zero elements, you can directly use this substitute using the xn and hn. Substitute hn instead of this unit impulse. You can also do it using the graphical method by plotting the hn and xn and then flipping hn and start shifting hn and multiplying with xn and adding. Let's do it here also. So here's xk. xk, as we said, is half at 0 and 1 at 1. So half here and 1 here. It's 1. So and this xk. And this time vector is k. And h n minus k, or let's say k equals minus, let's say 5. Sorry, at n equals minus 5. So we did a time reversal and then shift. So h n minus k equals h minus k plus n. Okay. Let's start by n equals plus 5, and you'll see why in a moment. So this will be this is k minus k, and then minus n, or minus 5 in this case. So we have done a time reversal and then shift by 5 to the left. So the signal will be, the impulse response will be, it will be just mirrored to the left and then shifted by 5. So instead of 0, it will start from -1, -2, -5. So let's say -1, -2, -3, -4, -5. We'll have one impulse, second impulse, third impulse. Like this, approximately. Now, what we'll do from this convolution sum equation, we need to multiply xk by hn minus k to find y at n. Now, n equals 5. So to find y at 5, we need to multiply those two signals and add the samples at all k indexes. So as you can see here, there's no overlap between those two signals. Then y at 5 will be 0. Okay. Y at 5 will be 0, and we keep shifting. Sorry, I think I have made another mistake. I think this should be -5. And here we have a plus. Then at k equals -5, let's see the 0, and you're shifting to the left. Yeah, because we have a time reversal. So -5, we're shifting to the left. So at y -5, we have 0. We have 0. And then we keep shifting. If we keep shifting to the left, we'll keep getting 0. So we'll shift to the right. Let's say at n equals -4, we'll get another 0, because those three impulses will be shifted by one time step to the right, and we still don't have any overlap until we have a n equals 0. Then we'll find the first overlap. So at y equals 0, at n equals 0, we'll have this impulse overlapped with this impulse, and the product between them is half, and we don't have any other overlapping. So y at 0 will be just half delta n, just one impulse at 0 with a scaling of half. And so on. We keep shifting the impulse response. If we shift it to n equals 1, now we have overlap with those two first impulses with this one and this one. So we'll have two impulses. One of them at 0 with amplitude half, and the other one at 1 with amplitude 1, delta n minus 1. And then y at 2, this impulse will not be overlapped, but those two, the last two impulses will be overlapped, and then we'll get also half delta n plus delta n minus 1. And if we shift one more time, we'll have two impulses not overlapped, and only the first impulse is overlapped with this impulse, and we get delta n minus 1. And after that, if we keep shifting, we'll start getting zeros because there will be no overlap between the HN, the impulse response and the signal, the HN minus K exactly, and XK. So after that is zero, before that is zero. So the signal that we have is uh, is actually exactly this signal that we have here.
I of n.
Yes, exactly.
I see.
In this example, we have Xn as two impulses, one of them at zero, the other one at one, and they are scaled differently, 1/2 and 2. And then also we're given the impulse response of the system in terms of unit steps. And then we have moved from this definition of the unit steps. If we just draw them, we'll find that this impulse response can be written as three impulses, 3 unit impulses, right?
Yes.
Yeah, I've just drawn the UN. It will be only non-zero in this part, and then UN minus 3 is shifted and then scaled by -1, and the signals will cancel in this part, and they are zero in this part. So what's remaining is just those 3 impulses at 0, 1, and 2. And then I have shown how to find the output using the convolution. First, I have directly applied this because this system's only or the input and the impulse response are not only non-zero at few time steps. So we can directly use this. We just replace those delta n's by hn in the
Yes.
xn, and we get yn because it's actually the definition of the convolution, which is just scaling and shifting the impulse response. It's the definition of the convolution. See how we shift the impulse response and scale it by xk. So we can do this directly, and we found the output like this.
Yeah.
Or we can apply the convolution, and since xk is only non-zero at k equals 0 and k equals 1, so we can directly, it's the same as this, the first line, right? It's x0 times hn plus x1 times hn minus 1. And x0 is half, x1 is 2, so we get the same, the same result, right?
And
For the last method, I'll do it again because I have made some mistakes here. You might help me as well if you are good with finding the convolution using the graphical method. Okay. So I was trying to find this yn using by doing the convolution using the graphical method. So first I have plotted the xk. It's the input signal, just one impulse at 0, one impulse at 1. And also the shifted impulse response, the time reversed and shifted. So hn minus k, when n equals -5, we get this.
right.
Right. And then we'll start, first we'll multiply those two signals and add, you see from the convolution, we have a summation for k from -infinity to +infinity. So we just multiply those two signals and add the values over all k values, over all the vector of k time steps. So we'll get y at -5, right? It's just the product of those two and the summation. And since they are not overlapping, we'll get 0. And the same when we shift by -4, shift by -4, so those three impulses will move one step to the right. And we'll get another 0, y -3, and 1 -2, y -2, and y -1 will be also 0. Is that right?
Okay. Is it because is it because h of n, no, wait, hold on. Y of, is it because h, when it's -4 or -3 or something like that, it's 0? Like it shows in the graph right there on the right side?
Yeah, because it's actually because this input signal is 0 at negative n, when n is less than 0.
Yes, I see.
Yeah.
Yes, yeah, okay, I see it now. Yeah.
So we keep moving this, we keep shifting the impulse response until -1, we have no overlap with the xk. So we keep getting 0. But at y0, we get
So we get 1/2.
This impulse will overlap with this one. So we get just half.
I see.
We get an impulse just one impulse at 0 with amplitude half.
One impulse. Let's see.
Right.
That impulse comes from the H graph, or does it come from the X? Because like I get that the 1/2 comes from the X graph.
But
The
those
X
are
of K.
impulses. Yeah. Those are impulses. So it's an impulse at 0 with amplitude half. Because
Oh, okay. Yeah,
because it's a
I see it.
discrete time signal. Yeah.
Okay. Yeah, I keep thinking that because we're not finding the impulse response, we're not finding, like, we don't have the step signals correct as our answer.
Yeah.
Never mind. Yeah, sorry. It's just
It's
never mind.
confusing but you need to practice a little bit.
Yeah.
It's just to signify that this is a discrete signal, and
Mhm.
to keep in mind the special definition of this impulse response signal.
So
Sorry,
graphically,
unit
it would
impulse.
look, I mean, graphically speaking, it would look like a upwards arrow, like that stops at 1/2 or something like that.
In continuous time, we usually write it as an arrow,
Mm-hmm.
but in discrete time, you just put a circle at this amplitude at half.
Got it.
Yeah. So if we shift one more time, we shifted one more time, then we'll have those two impulses overlapping with the xk.
Mm-hmm.
So what we'll get here is one impulse at 0 with amplitude half, and we get one impulse. The other impulse is overlapping with this one. It should has the amplitude of 1. And then this will be at n -1, right?
So it includes the, like, y of 0 for this one, like the 1/2. Sorry, because that's where because I'm confused on where the 1/2 of um impulse to the n comes from.
Sorry, I didn't get a question. Yeah, can you?
Like where does the 1/2 come from for the
You mean
previous
this
one?
one?
Yeah.
This one's because at this point we have both impulses are overlapping with those two. You
Then
know,
how come that doesn't apply for the y of 0 case?
y of
Right.
0, at y of 0, we have only this first one overlapped with,
Oh, okay.
we don't have
Okay.
any other overlaps, right?
Yeah.
Only the first one was overlapping, so we just got the first impulse, and then we moved one more step to the right. Actually, I'm not plotting, but I'm just imagine, like, you need to imagine this in your mind, that those three impulses are moving to the right.
No, I see it. I see it. I think I see it now because the rightmost impulse signal from h of n minus k when y equals 0,
Are
that like that merges with the x at 0.
Yeah,
And
it's
when
actually a multiplication. Yeah, we multiply them together.
yeah. Yeah, I can see it now. No,
Yeah,
okay.
and this summation, this addition is just from the definition of the convolution because it's a summation over k, right?
Mhm.
Okay. Now we have y1 and then y2 equals now this impulse will be not overlapping with those two impulses, but the last two will be overlapped with those two, right?
Right.
When we move one more step, so let me plot it here. Just I will remove it, what, just to see it. So you will have one here, one here, and one here, and the x k will be half and 1 and 0 here and 0 everywhere else. So we multiply those two, the red with the black, and then we add them together.
Wait, can you re-explain why for the graph it's three impulse like dots for that for h
Uh,
of n minus k?
yeah,
It's only
from here,
three.
you remember is hn is defined as yn minus 3.
Oh, I see. Okay.
So yeah, one of them is starting from 0 till infinity is 1. The other one is shifted by 3, and it's minus 1s. So they cancel. They are
Mm-hmm.
0 here, and they cancel after when n is larger than 3. And then what's remaining is just those three impulses.
I see. Okay, that makes sense. Thank you.
Yeah. Yeah.
I just need to see that. Yeah. All
And
right.
then to do the convolution, we flip them. We do the time reversal, and then we start shifting them to the right. Okay.
Mhm.
Then at y equals 2, we'll have the last two impulses will be overlapped with those, and then we'll get also half delta n plus delta n minus 1, right?
Mm-hmm.
And then when we have y3, y3 will be only the last one overlapping, right? Which is delta, sorry, which is half delta n. Last one's overlapping, half delta n. And then when y equals 4, we'll have nothing. Oh no, sorry, we still have this
Delta
left.
n minus 1.
Yeah, we still have overlap with this one. Yeah. We still have delta n minus 1. We have 1, 2, 3, 4. At y equals y0 is half delta n, y1 half delta n plus this, y2, y3. We are missing something. We're still missing one term of this. I think I have made a mistake somewhere.
Oh.
Right? Because we should get oh no, I think it's correct. We should get something like this.
The 1/2 delta n plus 5 over halves.
5, yeah, over 5 over 2 delta n minus 1, delta n minus 2, delta n minus 3. So currently we have 1, 2, 3, 4. I think those deltas should be written in terms of k. So this will be k, this will be k minus 1, k minus 2, and this will be k minus 2, k minus 3, k minus 3, k minus 5.
I'm gonna relook at my notes right now just to see if there's
Yeah.
something.
Delta k, and then delta k minus 1. Because it should be k minus n. K minus 1. Let's remove all of this stuff. Let me share this. So we started from xk, xk, which is just one impulse at 0, one impulse at 1, right? And hk is those three impulses, 0, 1, 2.
Mm-hmm.
Then from the convolution definition here, we multiply xk by hn minus k.
Yes.
and then we do the summation to get yn. So here at this step, we did n minus 1. So h minus 1 minus k, right?
Mhm.
H minus 1 minus k is u minus 1 minus k minus u minus 1 minus k minus 3. So, okay, we have written this in terms of impulses. So those three impulses are time reversed and shifted by 1 to the left, right?
Yes.
They didn't start from 0, they start from minus 1. And xk times h minus k,
There's no overlap.
it's
So
all
yeah,
0. So y minus 1 is 0.
yeah. Okay, that makes sense.
We
Yes.
get nothing. Similar to what we have got.
Yes.
Still here we were correct. And then we shift by 1, so it becomes h minus k,
Mhm.
because 0, n is
Yes.
0 here. And then yeah, we have the first overlap here
Mhm.
at 0, and then xk h minus k, hk where is hk is this one, doesn't change, we don't move it, so it's already, it has impulse at 0 and impulse at 1. So the product between this h minus k and xk it will result in just this impulse. Oh, I know what's the issue in my, we thought that this is 1. Do you remember?
Oh, it's supposed to be
Right?
2.
Yeah, it should be 2, and I have it 2 in the notes here. Oh, I have it 1 here. This is not correct. This should be 2. This should be 2. Yeah, because this should be 2.
Mhm.
Because yeah, this hn is correct. Xn is it's defined like this. So this is 2. The amplitude of this impulse is 2. Yeah, I think this is the issue. This part is correct, but the graphical one was not correct. So here at n equals 0, we got the first overlap. So y0 is half. And then we shift by 1 more. We have 2 overlaps, 1 at 0 and 1 at 1. So half plus 2 is
The 1/2 comes from when k is 0, correct? And then the 2 comes from when k is
1. Yeah, that's correct.
okay.
So 5/2, and then we shift by 1 more. And then we get also the last the last 2 impulses will overlap with xk, and then we get again 5/2.
This
Similarly,
assumes when n is like 0, like the h of 3 minus k, that's assuming n is 3, correct?
yes, this is n actually. Yeah, this is the
Okay.
time shift.
Okay. All right.
Now we have, like, we always dealt with the time variable as n, but here the time variable is k, and we are shifting by n. You know,
Mhm.
right? From the definition of the convolution, we have just changed the variable names. Now k is the time variable, and then we are shifting by n. Here is shift 3, shift 2, we have 2 overlaps. Shift 3, we have just 1 overlap, will be y3 equals 2. And then after that, we'll have no overlaps, and it will be 0. And then the yn will be this way. I think what I was doing wrong is that, you see here, when we have y0 is half, this is actually, here is correct. So this one should be written as half delta n. here, after we add them together, so 5/2 delta n minus 1, right?
So it's five halves. That's the magnitude or something like that times
The
delta.
magnitude of the pulse at delta n minus 1. And then here, the magnitude of the impulse at delta n minus 2, and so on. And here at delta n minus 3, you see, at delta n, we have just half. At delta n minus 1, we have 2.5. Delta n minus 2, 2.5. Delta n minus 3, we have 2, and then zeros.
So graphically, it's just the like the black like the ones with the black dots. That's just the culmination of all the purple ones, all the
Uh,
purple ones. Is that what
yes,
it is?
it's, yeah, because this is the product between this h after shifting with xk. This is the final product, so we just add them together.
Okay.
We add them. The addition is because of the definition of the convolution. You see here we have xk, and then we shift h by n, multiply them together, and add all the samples. Summation. We add them all together. Right?
Yes.
So let me do this quickly, just to make the notes complete,
Mhm.
and remove the confusion. At this at n minus 5. So let's start from n minus 1, similar to the notes. When n equals minus 1, I will draw those every time I move. I'll do new shifting. So at n minus 1, we'll have 3 impulses here. One here, one here, one here. So h minus 1 minus k equals delta k minus 1, right? Because here with k is the variable, plus delta k minus 2, plus delta k minus 3, minus 1, minus 2, minus 3. And this is h. And then x k h minus 1 minus k. And then we are doing the summation. This is from the convolution definition. We are adding those terms from, since xk is just non-zero at 0 and 1, and h minus 1 minus k is just non-zero at minus 3, minus 2, minus 1. So let's do the summation from k equals minus 3 to 0. Sorry, to 1. Do you see this?
Yeah.
Do you see
Yes.
why?
Yeah.
From minus 3 to 1, because we don't have any overlap. We have always zeros
Yeah.
outside
Yeah.
region.
Anything that's less than -3 would be 0. So that makes
Yeah.
sense.
So this will be, let's start from minus 3. X minus 3 minus 2 minus 1 is always 0. So we get 0 plus 0 plus 0 plus, when k equals 0, x0 will be half, and h minus 1 will be 1. So we have half times 1 plus, when k equals 1, xk or x1 is 2, and h minus 1 minus 1 is 1. So 2 times 1. Oh, but that one is not overlapped, sorry. Let me double check. I think I'm still it's missing again. K is minus 3 to 1. H minus 1 minus K is those three impulses. When K is 0, this will be 0, right?
Yes. Yeah. Same.
When K is 0, all of them are 0. When K is 1, this is the only one is 1, and the rest are zeros. When K is 2, this is 1. When K is 3, this is 1.
Yeah.
XK, when K is 0, it's half. When K is 1, is 2. So set n equals minus 1. Oh, but when we multiply them together, we don't have at. I think I'm confusing you. When n equals minus 1, so we are here. We don't have any overlap, right? When n equals minus 1, then the product will be 0 because we're multiplying those signals together, right? So there's no overlapping.
Mhm.
When K, but we need to find it here. When n equals minus 1, so this signal is here. It's just 3 impulses at minus 1, minus 2, minus 3, and xk is at 0 and 1, so xk h minus 1 minus k is always 0 for all k. When n equals 0, we have h minus k, which is delta h minus k, which is delta k plus delta k minus 1 plus delta k minus 3. Oh, yeah, that's this is minus k minus 1, minus k minus 2, minus k minus 3. This is minus k minus 1, minus k minus 3. Right? Because it's h n minus k. So yeah. So it will be, I'll update this figure. It will be one impulse here, one impulse here, one impulse here. Now, if we multiply those two signals, we have this overlap with the half. So y at 0 will be x at 0 times h at 0, which is half. Half times 1, which is half. Delta n or delta k. Or we can keep those till the end. Let's just find the amplitude. So the amplitude of, sorry, this is half. So this first impulse is at 0 with amplitude half. And we continue similarly. N equals 1. Then we have h minus k minus 1. uh, minus k minus 1. When n equals minus 1, we have minus 1 minus k. When n equals 1, we have k plus 1. Minus k plus 1, yeah. Which is, I'll update the figure again here. We'll have just one impulse here, one impulse at 1. Now, if we multiply those two signals, uh, we multiply those two signals, we'll have half times 1 and 2 times 1. So this is delta, sorry, yeah, delta minus k plus delta minus k minus 1 plus delta minus k plus 1. The impulses, one in the middle and one at minus 1, one at plus 1. And then y at 1 equals, as we said, if we multiply those together, there will be half times 1 and 2 times 1. So half times 1 plus 2 times 1, which is 5 divided by 2. At n equals 2, we move one step to the right, so we'll have this signal at 0, 1, and 2. And if we multiply those two signals together, we'll have half times 1 and 2 times 1. So y2 half times 1 plus 2 times 1, which is 5 by 2. And then n equals 3. When n equals 3, we don't have this. We have here 3, 1, 2, 3. And then if we multiply those together, we'll have just overlap here, which is 2 times 1. So y3 is 2 times 1, which is 2. So the output will have those four impulses, one of them with amplitude half, amplitude 5 over 2, 5 over 2, and 2, which is the same as we got in the previous method. So the output is yn is, as we have seen here, we have one impulse at 0, so with magnitude half, so half delta 0 plus 1 at 1, so 5 over 2 delta, sorry, not, this is n. So the impulse is at 0, n minus 1, the impulse at 1, plus 5 over 2 delta n minus 2, plus 2 delta n minus 3, the last impulse at 3. Yep. I'll solve one more example, and then we'll go through the homework. Or let me finish here because it's taking too much time. Let's answer your questions regarding the homework and stop here.